let us discuss about an AC circuit in which an inductor and a resistor is connected to an AC source. So, if we try to draw a circuit diagram, simple diagram, it might look like something like this. An inductor in series with a resistor, both of them connected in series to an AC source. The AC source is given by E is equal to E naught sine of omega t, which means that the peak value of the voltage is E naught and the frequency, angular frequency is omega out here, radians per second. Now, our aim is to find the value of current out here in the circuit. So, in order to find the current out here, if we can recollect that normally in case of a DC circuit, we normally write in DC circuit, we say the potential drop across, let us say the inductor, let us represent it as VL, and the potential drop across resistor as VR. This is what let us represent. Now, in a DC circuit, what we can say is E applied EMF is equal to sum of the potential drop across all the series components which are placed with the source. But in an AC circuit, this does not hold true. So, the question arises why? The reason is, if we try to recollect the previous discussions, we know that in case of resistance, if the current is this way, the potential drop across the resistor is in same phase as the current. If I try to represent in case of inductor, if this is the current, then we know that potential drop across inductor is 90 degree out of phase, which means that definitely we cannot go for algebraic addition. So, if we want to find the resultant, then if we superimpose these two in case of AC, so what we can see is, so in AC circuits, what we have is current out, I can represent the two potential drops on the same phasor diagram. It looks something like this. ER is this way and EL is 90 degree out of phase out here. Therefore, what we can say is the net which we represent as Ez square is ER square plus EL square. Clearly, that we can conclude, since the potential drop across the resistance and the potential drop across the inductor, they are 90 degree out of phase. So, by using the Pythagoras theorem, we can arrive at this result. Now, what is ER? We can write it as, say, I naught into R whole square, and we can write this as I naught into XL the whole square. So, this can be written as I naught, let us say, into Z the whole square. Now, what is Z out here? Z is impedance, net impedance of the AC circuit. It is the net impedance. Now, what is impedance? Impedance is a word which is synonymous with the resistance. Now, resistance is a word which is reserved for the DC circuits. Therefore, we have to use a synonym which is similar to resistance. So, in AC circuits, we are using the word impedance, and this has to be kept in mind. In the numericals, the words clearly tell us what type of source is if we understand these words properly. They are used in AC circuits. So, therefore, we can say I naught square z square is I naught square r square plus I naught square xl square. So, I naught square z square, take I naught square common out here. So, we get an equation r square plus xl square. So, from this we conclude net impedance is root of r square plus xl square. This z is said to be the impedance of RL circuit. Impedance. So, we can clearly see that impedance depends upon the frequency of the source, while the resistance in a DC circuit does not depend on it. This is exactly how we can find the net resistance in an AC circuit, that is the impedance. Now, the expression for the current. What will be the expression for the current? For the current in LR circuit, I is written as I naught sine of omega t. Till here we know the expression is going to remain the same, but now in case of R only circuit we know the phase difference was 0. In case of L only circuit we know that the EMF lags current by 90 degree. So, we had a minus sign out here. Now, here it will not be 90 degree, it will be some angle phi. This phi lies between 0 degree and 90 degree. So, the question arises, how much will be phi? How to find that? So, if you go back to the impedance triangle, what it was, this is exactly how the current I, this is exactly how we had ER and we had EL here. So, the resultant lies somewhere here like this. This angle is said to be phi. So, from this impedance triangle, what we can say is tan of phi is EL by ER. So, that can be written as I naught XL by I naught R. So, we get therefore tan phi is XL by R. That is exactly how we can find the phase relationship between the EMF and applied EMF and the current. Now, so what we can conclude here is, in case of R only circuit, the current lags EMF by an angle phi, and the angle phi is given by the expression tan phi is XL by R. Now, the next thing that we have to find in an LR circuit is power consumption. So, how to find the power consumption? In order to find power consumption, we know that power is given as E into I. Both applied EMF as well as current are functions of time. Hence, what we get is instantaneous power. The instantaneous power is given by P is E into I, wherein E is E naught sin omega t and I is I naught sin of omega t minus phi. Now, we have to find, this is instantaneous. So, we can write it this way, E naught I naught and sin omega t into sin of omega t minus phi. We can write it as sin A cos B minus sin B cos A. This is how we can write. Now we can also simplify it further. It can be written as E naught I naught, then sin omega t. So out here I get sin square omega t into cos phi minus sin phi into sin of omega t into cos of omega t. This is how we can simplify. Further simplified, we can write it as E naught I naught sin square omega t into cos phi minus E naught I naught by 2 and sin phi, and I can write this as sin of 2 omega t. Closely observe, this equation of instantaneous power is function of time. So now our aim is to find average power. So therefore average power will be what? Average power is, we have to find integration of instantaneous power P dt over the complete cycle upon 0 to t of dt. So if we try to simplify this, we get an equation like this. First term is E naught I naught, denominator is t, and cos phi sin square omega t. This is first term minus E naught I naught by 2t and sin phi and sin 2 omega t. This is what we get. This is to be integrated from 0 to t. This is from 0 to t. So writing it in a proper way, we can write it this way: E naught I naught by t cos phi from 0 to t of sin square omega t dt minus E naught I naught by 2t sin phi integration from 0 to t of sin of 2 omega t dt. Now we know that integration of sin square omega t by using the normal methods of integration by substitution or by integration by simplification, we have seen this. This comes out to t by 2, while this integration of one complete average value of a complete sine wave is 0. So therefore P average comes out as E naught I naught by 2 into cos phi. So write it in the proper form. So this can be written as E naught by root 2, I naught by root 2 and cos phi. What is E naught by root 2? This can be said as ERMS, IRMS, cos phi. So therefore average power of an RL circuit is ERMS, IRMS into cos phi. This term cos phi is known as power factor. So therefore power factor we get as cos phi. Remember, phi is not the power factor is cos phi. So cos phi from the impedance triangle can be said as XR, that is cos phi can be said as ER by EZ. ER is I naught into R, this is I naught into Z. So power factor cos phi works out as R by Z. That is exactly how we can find out power factor of an LR circuit. We can find out the expression for the current in an LR circuit. We can also find out what is the phase difference between the current and the EMF in an LR circuit. Now, let us take one numerical which is based on the concept of LR circuit. The question is like this: the current and voltage in a circuit is given by the expressions I is 3.5 sine of 628t plus 30 degrees amperes, and voltage is given by E is 28 sine 628t minus 30 degrees volt. So, the question is identify the two pure elements in the circuit and then find their values. So, let us try to solve this problem. Okay. Now, if we see the expression for the current and the EMF, phase of current is given as plus 30 degrees and phase of EMF is given as minus 30 degrees. So, therefore, phase difference is, let us say, phi I minus of phi E, that gives 30 minus of minus 30, which means 60 degrees. And by seeing, we can say current is leading here. So, EMF lags, current leads here. So, when the current leads, this clearly shows, this means current I leads E by 60 degrees. Now, if current leads, so what we can say, therefore, it is a RC circuit, because in RL circuit current lags EMF by some angle, while in a RC circuit current leads the EMF by 60 degrees. That is exactly how we can identify the two elements.